Alright, AP Chem class, welcome to Chapter 10, which is Chemical Bonding 2, Molecular Geometry. Hopefully you remember some of this from Gen Chem. Hybridization of atomic orbitals was something we did a little bit in Gen Chem, so I hope that a lot of this is review for you, and we're going to progress through pretty quickly on it. So, we're following VSEPR model, which is valence shell electron pair repulsion model. Basically means electron pairs repel each other, negatives and negatives do not want to be together, like charges repel. So we can predict the geometry of molecules from their electrostatic repulsions between the electrons, bonding and non-bonding pairs. Pretty wordy, pretty easy to do. So let's start right into it here. If we start with AB2, this just means one atom to two different atoms. So our number of atoms that are bonded to our central atom is 2, because this would look something like this maybe. A is bonded to B, and on the other side is bonded to B, and it has no lone electron pairs or anything crazy in there. It's just like this. So our number of lone pairs on the atom is 0 because A is just bonded to B like so. So our arrangement of electron pairs would be linear, which basically means if you look at this whole molecule, what's the shape of it? You know, is it a square, pyramid? It's a line. B to A to B is a straight line. So our angle between the two bonds of a straight line is 180 degrees. It's straight. So our molecular geometry, we call this shape linear. Pretty easy stuff. So our example of that is, here's what I drew for you, AB2. They do beryllium chloride, so beryllium is A, chlorine is the B2 part. There's no unbound electrons here on beryllium, but there are on chlorine, these lone pairs. But those don't matter so much because the bonded atom in the middle, its angle's 180. It's a straight line. So hopefully that's pretty easy. So let's move on. AB3. So how many are bonded? Well, 3 of them are bonded. Lone pairs, 0. Maybe boron trihydride would be an example of this. So if you're looking at this, and this is A, and this is B, and this is B, and this is B, then our angle, if we take 360 as a circle, and we cut it into thirds, then we get 120. That's the angle between two bonds, or the bond angle. And so we call that trigonal planar. Trigonal, 3 sides, 1, 2, 3. Planar meaning they're existing on a flat plane. So we don't have any of these bonds. They're not coming out towards you from the screen, and they're not going back into the screen. They're all just really flat, like they are here on the screen. So here's what that would look like: 3 in a flat plane, trigonal planar. They give you boron trifluoride. So boron's here, fluorine, 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 120 degrees, and it's pretty symmetrical. So AB4. So we have 4 that are bonded to A, and 0 electron pairs. This could be like methane, maybe C in the middle, and then C's got 4 atoms around it, and they're all kind of equal distance away from each other. So there's a hydrogen there, and a hydrogen there, and a hydrogen here, and a hydrogen here. And so then carbon has its complete octet, and we don't have any unbound valence electrons to mess with our shape. And so this is just 4 sides, AB4, no lone pairs on it, and we would call that a tetrahedral shape. So 1, 2, 3, 4, 4-sided, call that a tetrahedron. And it gives you your bond angle here to 109.5, and then here your shape is tetrahedral. So hopefully that's pretty easy. Here, methane, same thing, CH4. So carbon, hydrogen, 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 hydrogen. And here you say, why can't we take 360 and divide it by 4 to get our angle? Well, here we're not just in a flat plane. Now we are using that 3-dimensional. So this kind of hydrogen here would be coming out of the screen towards you. This hydrogen here would be angled back into the screen. This hydrogen's angled back into the screen a little bit, and this hydrogen's running straight up, kind of perpendicular to the screen. And so we start to think 3-dimensionally, it changes our bond angles a little bit. But that's more realistic. So AB5, we have 5 that are bonded to the central atom with no lone pairs. We call that trigonal bipyramidal. So 3 sides, because around A is 1, 2, 3. But now we kind of have a pyramid on the top. If you look at these red lines that they've drawn in between the bonds, you have a pyramid on the top, a pyramid on the bottom. So we got 3 bonds, but it's bipyramidal, 2 pyramids, one on the top, one on the bottom. So trigonal bipyramidal is our molecular geometry. So this would look like phosphorus pentachloride. Here you can kind of see where they're getting that idea of a pyramid up here and a pyramid down there. And their bond angles are going to have some that are at 90 and some that are at 120, kind of depending on which one you're looking at. So AB6, if we have 6 atoms bonded to the central atom and no lone pairs, then we call it an octahedron. And so here the goal again is to get those electrons as far away from each other as possible. They don't want to be around each other. So we start with 4 in a flat plane. Then we do 1 up, 1 straight down, and they're as far away as they can. And when they connect all of those, we end up getting an 8-sided figure. 1, 2, 3, 4 on the bottom, 5, 6, 7, 8 on the top. That's octahedron. So here you have an octahedron. So we call it octahedral, 8-sided shape. And so here's your example for something with AB6 would be sulfur hexafluoride. Sulfur's in the middle. There's 6 fluorines all around it. And you can see we're pretty much in a 90-degree bond angle. And so here they are kind of comparing them how the shape changes, I guess, as you add different atoms, more atoms bonded to the central atom. Oops, sorry about that. There we go. Alright, so now let's look at if we take away what was a bonded atom and we make it unbound electron pairs. I want you to notice the size of this kind of space filling model. This red area represents the negative electrons taking up space compared to the green space required to form a bond. You notice that the green space to form a bond is pretty small. These electrons aren't that space greedy. An unbound electron pair is incredibly space greedy, and because electrons repel electrons, these unbound electron pairs will shove the other electrons away from them. So here everybody was kind of playing nice, and we had this nice sort of symmetrical tetrahedron. Now as we add lone pairs with NH3, these electrons here we can think of as taking up so much space and being really greedy and exerting a force, a repelling force on all these other hydrogens. And instead of getting this nice wide 109.5 where we're really symmetrical, we're going to crunch them down to about 107.3. And these little electrons that are being shared between nitrogen and hydrogen aren't as space greedy as these electrons here, so they're pushed down to 107. And now here we get water, which we're really familiar with. We have unbound electron pair, really, really space greedy. Another unbound electron pair, really, really space greedy. And so they're going to be repelling these hydrogens. And they're going to push those hydrogens in even further than one unbound electron pair. 2 unbound electron pairs really push on them. So now we're going to crunch that angle down to 104.5. And then we start to get to a point where these electrons are repelling each other here as well as these electrons are repelling the bonded electrons. And so we kind of find that happy medium at about a 1.45, or 104.5 rather. And so that's how having unbound electrons affects your geometry. So we're going to affect our geometry here. This isn't tetrahedral anymore. We've crunched these angles down. We've got to call it something different. And this is no longer linear. Even though it's hydrogen, oxygen, hydrogen, it's not a straight line. It's bent, and that's because of these unbound electrons. So they affect our geometry a little bit. There, it's circling bond angles to show you that they're shrinking, which I've already explained. So let's look at how we change this stuff. We start with AB3, which was 3 bonded atoms and no lone pairs, and it's trigonal planar. Well, let's change that to AB2E. So A stands for the central atom, B stands for another atom, but E stands for electron pair now. And so now we can say we've got 2 atoms bonded and 1 electron pair. And so what will that look like? Well, 2 atoms bonded, 1 electron pair. We say it's got a trigonal planar arrangement of electrons, but that is not the molecular geometry. What you're going to be asked about is going to be molecular geometry, and that would be bent. So here's sulfur dioxide, bonded to oxygen, bonded to oxygen. Lone electron pair is going to bend those down. So AB4. Let's change that. We had that nice tetrahedron. Let's change that to 3 bonded atoms and an electron pair. Now we have 3 bonded and 1 electron pair. Well, what's that going to look like? We're going to push those 3 atoms down a little bit, and we're going to call that trigonal pyramidal. Hopefully that name makes sense. Trigonal, 3 sides. We still have 1, 2, 3 sides to this, But because that electron pair is so space greedy, we're going to shove those legs down like the legs of a pyramid. So trigonal pyramidal. So let's look at another option. If we're looking at four regions, I guess you could say, bonded to the central atom, we could make two of them atoms and two of them electron pairs. Now you've already seen this shape, so hopefully you can predict it. What's one we've seen that had a central atom, two other atoms, and two electron pairs? Hopefully you're thinking water, because you'd be right. So we've got two that are bonded, two that are not, so it's going to look like this. Push those B's down and two electrons here. A is in the middle, and we've got a bent shape like we had with water, and so that's what we call it, bent. Water was our example, and here you can see it's bent. So AB5, now we have a lot of bonds to work with. First option, one lone pair of electrons and four other atoms gives us 4 and one lone pair. We call that trigonal pyramidal for electron pairs, but not for shape. Our shape, this is some weird one. Distorted tetrahedron is its name. Awful to memorize, but it does actually kind of make sense, because if you have 4 attached to it, that should make you think tetrahedral. But because this electron pair is pushing, this guy should kind of be up here, but that electron pair is really pushy, so he shoves them down here. You get this goofy looking tetrahedron. So it does kind of make sense, even though the name is weird, a distorted tetrahedron. So let's put 2 electron pairs on there and only have 3 bonded atoms and see what that looks like. Well, here they're sticking with showing you that all of our electron pairs, because we're always adding up to 6 basically, is always trigonal bipyramidal, but those aren't molecular geometries. And what you're asked about is molecular geometries. So this is neat, but this is important. And so here, this AB3E2, we've got 2 electron pairs, and those aren't really that important when it comes to your molecular geometries, naming at any rate. So our name comes from this one line, and one in the middle, and that's T-shaped. T-shaped. Look at that molecule. ClF3. Weird, right? Chlorine trifluoride. Alright. Well, okay, so T-shaped. That's what that's called. So there's another option. Lots of electron pairs and only 2 bonds. And so if we only have 2 bonds and 3 lone pairs, we get something like this. A line. Electron pair, electron pair, electron pair, all repelling each other, rather. Sorry about that. And then we just have 3 in a straight line. So that's linear. And their example there is iodine bonded to iodine bonded to iodine with a -1 charge. So we're getting into stuff that is important, but isn't something you see very often. You don't see these super frequently in the problems that we're going to do. So I don't know if I would lose any sleep in committing those to memory. Here's when you see a little bit. AB6. So just 6 that are bonded, an octahedron. If we make 1 electron pair and we have 5 bonded and 1 electron pair, then we get this shape, square pyramidal. So before we had a pyramid with 3 sides, now we have 4 in a flat plane and this 1 bond going straight up, and so it kind of makes a square-based pyramid, which sort of makes sense. If we have 2 electron pairs, then we have 4 bonded, 2 unbonded. Then again, we still have the octahedral electron pairs, but our shape is square planar. And this one I think makes even more sense. Weird compound, right? Look at this, making a compound with a noble gas. Wow. But there you have it. So xenon in the middle, fluorine, and then these electrons want to be about as far away as they possibly can. They're super space greedy, and because they have sort of an equal power to repel these guys, they end up being square on a flat plane, and so square planar is a name that's pretty logical. And so here's kind of a chart in your book that kind of breaks these shapes down for you. So how do we predict this? If you're given a problem and asked to predict it, which you will be, here's how you do it. First thing you do is draw your Lewis structure. Second thing you do is count your number of lone pairs and the number bonded. Use your valence shell electron pair repulsion to draw it and figure out how far apart that geometry can be. And so we can draw these things like SO2 and SF4. So we make a bond with sulfur, sulfur dioxide here. We got a double bond on one oxygen, a single bond on another, and the lone pair above the sulfurs. And so then we can look at its shape and say, okay, what is it if you have 1 bonded, 2 bonded, and 1 lone electron pair? That'd be AB2E is the way you'd say that. And there it is. And we'd know that that's a bent shape. Now, sulfur tetrafluoride here, we've got sulfur with 2, 4, 6, 8, and then the lone pair 10. And so that lone pair is going to kind of distort these a little bit. And so you'd have to say that's AB4E. And then you could look at the chart or memorize them and say, well, that's a distorted tetrahedron, where we push those 4 down a little bit. So let's talk about polarity, and then we'll call it good for one set of notes here. Dipole moments. If you have a dipole moment, then you're polar. If you have a permanent dipole moment, then you're polar all the time. Even nonpolar molecules get little tiny fluctuations in dipoles. They just don't last very long. And so here you have hydrogen bonded to fluorine. Super, super, super greedy fluorine is going to be hanging onto those electrons pretty much all the time. And hydrogen is going to be an electron poor region. And so we can say that it has polarity with delta plus, that's a partial positive on the hydrogen end, and a delta minus, a partial negative on the fluorine end. And so here we have Q is the charge and R is the radius between the charges. So, behavior of polar molecules. If you don't have a magnetic field on, they have a little bit of attraction with positive to negative, but overall the whole sample has no noticeable polarity. When you turn a magnetic field on, then they all line up. Negatives here, positives here. These molecules will kind of line up together, and that's how you know if something's polar or not. So, how do we know if we get resultant dipole moments? So if somebody asks, is this polar or not? Tell us why. You got to look at differences in electronegativities and symmetry of a molecule. And so here you say, okay, nitrogen is more electronegative than hydrogen. And so those electrons are going to be more towards nitrogen. So we draw our crossed arrow notation from hydrogens to nitrogens. And then we say the lone electron pair, there's a lot of electronegativity up there because their electron's not bonded to anything. So we draw an arrow from nitrogen to the lone electrons. And so we kind of look at these vectors and we're like, okay, we got up, 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 up. So overall, I would say this molecule would have something that looks kind of like this for a crossed arrow notation. Pretty much heading up to those valence electrons up there, and that's the resultant dipole moment. So your answer would be, yeah, this is a polar molecule, and this is the direction of its polarity. And here you can see the space filling model, the blue electron poor and the red electron rich, that is the case. Now, you look at NF3 and it gets a little bit trickier because our first arrow, they show that from nitrogen to the electrons, the arrow goes up. That's correct. It goes up towards these unbound electrons. But here, from nitrogen to fluorine, fluorine's more electronegative than nitrogen. Fluorine's more electronegative than nitrogen. Fluorine's more electronegative than nitrogen. So you say, is it polar? Well, yeah. I mean, it's not symmetrical. It's got unbound valence electrons. It's got to be polar. But which way do you draw the arrow if I have one arrow going up and some arrows going down? Well, since there's 3 arrows going down and only 1 arrow going up, you can imagine like if charge was a box and I had 3 people push the box this way and 1 person push the box this way. It might look something like this. Here's the box. 3 people push this way. 1 person, 2 persons, 3 people, and only 1 guy pushing this way. Whoops, my arrow went a little crazy. There we go. That's a bad arrow, sorry. Which way is the box going to move? Well, it's going to move. The net change is going to be this way, kind of slowly, because this guy's pushing back. And so here you can see they've drawn their resultant dipole moment down towards the fluorines, but the line is a lot shorter than here, where we had a really strong dipole moment. Here we're still going to have one. It's still going to be polar, but it's going to be weaker. So here you can see 1.46, 0.24. Is it polar? Sure it is, but not as polar as this one. And you can see in the space filling model, we've got red, we've got red, we've got red. So it's a little bit trickier, but you can still figure out the arrow if you take your time. So which of the following have a dipole moment? Well, you can take a minute and draw, and you'll figure it out pretty quick. So here, unbound valence electrons, we're pretty certain that's going to have a dipole moment. You can draw arrows and say, okay, well, oxygen is more electronegative than hydrogen, so there's a crossed arrow there. Oxygen's more electronegative than hydrogen, there's a crossed arrow there. And these electrons would be kind of up here, and so we know that it's polar. Dipole moment. Now this one is a little bit trickier. Here we got carbon dioxide, and you can look at it and say, boy, that thing's pretty symmetrical. Oxygen is more electronegative than carbon. Oxygen is more electronegative than carbon. And so really I would say this is going to be nonpolar because you've got the arrows, you can sort of think of them as canceling each other out. And so there they are. No dipole moment. It's a nonpolar molecule. So you look at this one and tell me if it's going to be polar or nonpolar. Alright, well hopefully you figured it was polar. Right away you see these two electrons up here, and you know that we're not really going to be very symmetrical. So oxygen and sulfur, which is more electronegative, you can draw your arrows that way. It's going to be going towards oxygen. And then these two electrons here are going to be more negative, and so we've got the net change is going to be one little arrow up here, two big arrows down to oxygen, so it's going to be a polar molecule. Now here, we're pretty symmetrical. We got the same pole to this fluorine, same pole to this fluorine, same pole here, same pole here. So when you draw these arrows, they kind of cancel each other out. That guy's going to be non-polar. If we cut him in half, he's got two fluorines on each side. Cut him in half, he's got two fluorines on each side. And so that is a non-polar molecule. No unbound valence electron pairs, you'll see. So, how about boron trifluoride? Does it have a polar moment? Well, let's take a look at it. Let's draw it. We remember boron the moron is happy with 6. So 1, and then 2, and then 3. That's 1, 2, 3, 4, 5, 6. We draw some fluorines. Sloppy fluorines. We draw some fluorines, and then we can of course complete their octets. 1, 2, 3, 4, 5, 6, something like that. 1, 2, 3, 4, 5, 6, something like that. Okay, you do that around all those, and you say he's pretty symmetrical. Fluorine is going to be more electronegative, so it's going to pull the charge that way. Fluorine's more electronegative, it's going to pull the charge that way. Fluorine's more electronegative, going to pull the charge that way. No unbound electron pairs, it's going to be nonpolar. And we would be right. So that is where we will end for